Today I'm going to talk about properties of exponents and how you can use them to simplify expressions. Now let's start with the most basic kind of an exponent, which is a positive whole number exponent. Now if n is a positive whole number, then b to the n power would equal b times b multiplied times itself n times. Now in this case, the number b is called the base and the number n is called the exponent. For example, 2 to the fourth power would mean 2 times 2 times 2 times 2. So when you multiply that together, the answer would be 16. Another example would be negative 3 to the fourth power would be negative 3 times negative 3 times negative 3 times negative 3. And when you multiply those all together, it comes out to be a positive 81. Now be careful. If you had negative 3 to the fourth with no parentheses written in there, the implication is that it's only the 3 that's being raised to the fourth power. So there's an implied set of parentheses right here. I'll put it in red. So what it would mean is that you're going to take the opposite of and then 3 times 3 times 3 times 3. So it would be the opposite of 81. And the answer would actually be negative 81. So be careful with that last example because sometimes people have a tendency of missing that. Now exponents can also be zero or negative numbers, and that's a little less intuitive because you can't multiply a number times itself a negative number of times. So we have to try to look at that in a little bit different way. And to do that, I'd like you to consider the following pattern. I'm going to start with the base of 2 and raise it to a power of 3. So 2 cubed would mean 2 times 2 times 2. And obviously that comes out to be 8. Now each time I go down one row here, I'm going to lower the exponent by 1. So this time I'm going to have 2 to the second power. So that would just be 2 times 2, which is 4. Notice I've multiplied by 2 one less time, and therefore the answer is 1/2 of what the original answer was. So in other words, this answer is 1/2 of the previous answer because I multiplied by 2 one fewer time. Alright, let's continue this pattern. I'm going to lower the power by 1 again. And 2 to the first would just be 2. You can see this pattern is still the case. This new answer, 2, is 1/2 of the previous answer. And that's because I've multiplied by 2 one fewer time. Now this pattern should continue. So if I lower the power by 1 again, I'm now down to a 0 exponent. And if this pattern is going to continue, my new answer right here that I'm looking for should be 1/2 of my previous answer. Since my previous answer was 2, what's 1/2 of 2? Well, the answer would be 1. And that's why that when you raise something to a 0 power, you get 1. Now let's keep going here. If I take 2 and raise it to the negative 1 power, the answer should still be 1/2. In other words, this new answer should be 1/2 of my previous answer. What's 1/2 of 1? Well, the answer is 1/2. And so I get the fraction 1/2 as that answer. And to continue this a little farther, if I take 2 to the negative 2 power, again, the new answer should be 1/2 of the previous. So the question is, what's 1/2 of 1/2? Well, if you think of the word of meaning times, it's really 1/2 times 1/2. So it's 1/4. And then 2 to the negative third power should be 1/2 of 1/4, which again is, think of as times, 1/4 times 1/2, so it's 1/8. Now notice there's a pattern here. 2 to the third power was 8 at the beginning. If you look way down at the bottom, 2 to the negative third power is 1/8. So notice those two kind of match up. They're reciprocals of each other, 8 and 1/8. Similarly, 2 to the second was 4, and 2 to the negative second was a quarter. Those are also reciprocals. And the other pairs of reciprocals would be 2 to the first and 2 to the negative first. One of the answers is 2 and the other is 1/2, so they're reciprocals. And this zero exponent, in a sense, lays right in the middle of this chart and equals 1. Now the important things to take away from this is that when you raise a number to a zero power, the answer is always 1. And when you raise a number to a negative exponent, the answer is a fraction. It's not a negative answer, but it's a fractional answer. So we can write down some properties. If we assume that b is not equal to 0, okay, because these properties wouldn't be true if b was 0. But as long as b is any other number other than 0, then b raised to the 0 power always equals 1. So that's an important thing to know. And also, if you take b and raise it to a negative power, that equals 1 over b raised to the corresponding positive power. That's another really important one. And a third one is if you had 1 over b to the negative n, that should be the reciprocal of b to the negative n, and that's going to come out to be b to the positive n. Now let me just give you a few examples. Let's say we had 5 to the 0 power. Well, that would equal 1. In fact, remember, any number raised to the 0 power would equal 1. The only one exception to that is 0 to the 0 power, and that happens to be undefined. Now let's say we had 3 to the negative 2 power. Well, using our property here, that would be the same as 1 over 3 to the second power. And since 3 to the second power is 9, that should be 1/9. Notice we get a fractional answer for that one. Okay, another example. Let's say we had 1 over 5 to the negative third power. Well, according to this third property, that would be the same as 5 to the third power. And 5 times 5 is 25, and then times 5 again would be 125. Now let's say we had 2 to the negative third divided by 4 to the negative 2. Now, because of these two properties here, what it basically allows us to do is take something with a negative exponent in it, and if it has a negative exponent, we can move it down to the opposite location and make it a positive exponent. So that 2 to the negative third will become a 2 to the positive third in the denominator. And similarly, this 4 to the negative 2, if we move it to the opposite location that it's in currently, it would become 4 to the positive 2. So this is actually really important to understand, is that when you're working with a fraction that has negative exponents, you can eliminate the negative exponents by moving each part to the opposite location that it's in. So if the negative exponent is in the numerator, move it down to the denominator and the exponent will be positive. And if the negative exponent is already in the denominator to start with, move it up to the numerator, and again it will become positive. The only time you can't do this is if you have addition or subtraction inside your fraction somewhere. But we don't have that, so we can do it here. Now we'll just simplify each part. So 4 to the second would be 4 times 4, or 16, and 2 to the third is 8, and 16 divided by 8 would be 2. Now I'd like to go over some properties of exponents. Now the first one is that if we have a base to the m power multiplied times b to the n power, that will equal b to the m plus n power. So, for example, if you had x to the second power times x to the third power, that will be x to the fifth power. Now the second property is that b to the m divided by b to the n will equal b to the m minus n power. So if you had y to the sixth divided by y to the second, you'd subtract the exponent. 6 minus 2 would be 4, so it would be y to the fourth. The next property is if you had b times c as a quantity inside parentheses to the nth power, that's the same as having b to the n times c to the n. So, for example, let's say you had 2x in parentheses, and the whole thing was raised to the third power. That would be the same as having 2 to the third power times x to the third power. And 2 to the third power is 8, so you'd want to take that all the way out to 8x cubed. The next property is that b over c as a quantity to the nth power equals b to the n over c to the n. So you can apply the exponent to the numerator and denominator separately. So, for example, if you had x over y and the whole thing was raised to the fourth power, you could say that's x to the fourth over y to the fourth. And the last property is that if you had b to the m inside parentheses and the whole thing was raised to the nth power, you multiply your exponents and it equals b to the m times n power. So, for example, if you had x to the fourth and that was inside parentheses and the whole thing was to the fifth power, that would be x to the 20th, because you'd multiply 4 times 5 to get 20. Now we'd like to be able to use the properties I just went over to be able to simplify expressions. And before we do some examples of this, let's be clear about what we mean when we say that we're going to simplify expressions. Number one, it means we're going to make sure we've removed any parentheses. Secondly, it means we've removed any negative exponents from the expression. It also means we would combine any like bases, whether they're in the numerator or denominator or one of each. And lastly, it means you would have evaluated any numerical expressions. So for example, if you had 7 squared in your expression, you should write that as 49. And if you had 7 to the negative 2, you'd want to first remove the negative exponent by, switching its location within the fraction and then simplifying it. Okay, so let's do some examples now. In this example, you see we have parentheses. And when you have parentheses, you want to remove those first. And remember, the way to do that is you're going to multiply the exponent that's outside by the one that's inside. So 7 times 2, that would be 14. 3 times 2 would be 6. And even on this 4, that 4 really has a first power on it. And so you're going to multiply 2 times 1. So it'll be 4 to the second, b to the sixth, and c to the 14th. And then in the second one, you do the same thing. So remember, this is 2 to the first, so you're going to multiply 1 times 3 and 3 times 3 and 4 times 3. So it would be 2 to the third, b to the ninth, and c to the 12th. Now remember, we want to evaluate any numerical expression, so 4 to the second would just be 16. So 16, b to the 6th, c to the 14th, times, and then 2 to the third would be 8. So 8, b to the 9th, c to the 12th. And now we're going to multiply. So 16 times 8 is 128. So you'd have 128. And then b to the 6th times b to the 9th, you'd add your exponents there since you're multiplying like bases. And so 6 plus 9 would be 15. So b to the 15th. And then the same thing with the c's. C to the 14th times c to the 12th. You'd again add 14 plus 12. And so that'd be 26. And that'd be your simplified answer. Now let's just check real quick that we've done these four things. We've removed parentheses, because there isn't any parentheses in our answer. There's no negative exponents in our answer. In fact, this problem didn't have any negative exponents, but some of the ones we do will. We've combined the like bases when we could. For example, we took the b to the 6th times the b to the 9th, and we combined them into b to the 15th, and we did the same thing with the c's. And we evaluated numerical expressions. So, in other words, we took the 4 squared down to 16 and the 2 cubed to 8, and we multiplied the 16 and the 8 together to get that 128. So we've done all those steps. Okay, let's look at this next example. Now this is a fraction, and you can see there are some negative exponents. And usually the first thing you're going to want to do is remove parentheses when you have them, but we don't have any parentheses here. And usually the second thing you're going to want to do is get rid of any negative exponents in your problem. For example, this d to the negative 7th power, if we bring that down to the bottom, that will become d to the positive 7th power. And with the ones that are already in the bottom, this d to the negative 2, we'll want to bring that up to the top and make it d to the positive 2. And this b to the negative 6th, we're going to want to bring that up to the top and make it b to the positive 6th. Be careful, this 24 here stays in the denominator. That's not connected really to that b to the negative 6th, because 24 has its own exponent, and that's a 1. It's 24 to the first power. So the first step would just be to rewrite everything without the negative exponents. So we would have 18 b to the 5th, and then I'm going to go ahead and squeeze in that b to the 6th right there. And then we have c cubed, and then we'll have d to the 2nd power. And that's going to be all over 24 c cubed d to the 7th power. Now the next step would be to combine all the like bases together, and also to reduce that fraction. So I'm going to kind of circle the parts that could be combined. We have a d to the 2nd and a d to the 7th. Now those are the same base because they both have a base of d. You have d here and d here. So those can be combined. You also have a c cubed and another c cubed. You have a b to the 5th and a b to the 6th that are right next to each other in that numerator. And then we have the 18 over 24. Now let's carefully go through each one of these. I'm going to put my answer down here. Now let's start with the fraction, 18 over 24. Now in this case you want to reduce that down just like a normal fraction. So let's just divide both of these by 6. So 18 divided by 6 would be 3, and 24 divided by 6 would be 4. So that would be 3 over 4. So I'll just put a 3 in the top and a 4 in the bottom here. Now let's combine these b bases. You have b to the 5th times b to the 6th. And since they're side by side, they're being multiplied, you would add the exponents. And that would give you b to the 11th power. Now the next one to look at are the c's. Now notice they're both to the same exact power, c cubed in the top and c cubed in the bottom. So they are actually just going to be canceled out. And there's not going to be any c in our answer at all. C cubed, remember, if you subtracted the powers, 3 minus 3, you would get c to the 0, which is 1. So you're really just multiplying by 1, which doesn't change the answer, so you don't even have to write it down. They just cancel completely out. Now let's look at the d's. We have a d squared in the top and a d to the 7th in the bottom. Now the easiest way of combining these two bases, when one's in the top and the other's in the bottom, is we know we have to subtract the powers. But how are we going to subtract them is the question. Do we take 2 minus 7, or do we take 7 minus 2? And that depends on kind of how you want to look at it. But here's how I think is the easiest way to go about this. Always take the larger power, 7, and subtract the smaller. So 7 minus 2 will give you a positive 5. And then put the answer wherever the larger power was originally. And since the larger power is in the bottom, that means we'll write our answer in the bottom. So we'll have a d to the 5th on the bottom. Now let me just highlight that again because that's really important. We can subtract the smaller power from the larger power. Okay, so that'll give us a positive answer because remember, we're trying to eliminate any negative exponents. So by doing that, by subtracting the smaller from the larger, we'll automatically get a positive exponent. But then we have to remember to put your answer where the larger power was in the problem. In our case, the larger power was in the denominator, and that's why we wrote the answer in the denominator. So you see, we've done everything we can do to simplify this, and that would be our final answer. Okay, let's look at one more example of this type. Now in this case, we have a whole fraction that's in parentheses raised to the negative third power. So we're going to want to remove those parentheses. And the way we can do that is, remember, when you have a fraction in parentheses raised to a power, you can apply the power to the numerator and denominator separately. So let's start by doing that. Okay, so you see I've placed the numerator and the denominator both to the negative third power. But we still have those parentheses there, and we want to get rid of those. But now that we've done that, we know that we can multiply the exponent on the outside by the one that's on the inside in each case. And remember, these numbers really have one exponents. So when we multiply each exponent on the inside by the one that's on the outside, and we'll do that in the denominator too. Let's write down what we'll get for that. So we'll have 8 to the, and then we have 1 times negative 3, so negative third. And then b, negative 2 times negative 3 is a positive sixth power. And then c, 2 times negative 3 is a negative sixth power. And then in the denominator, we'll have 12 to the 1 times negative 3 is negative 3. And b raised to the negative 5 times negative 3 is positive 15. And then c raised to the negative 3 times negative 3 is positive 9. Now, once we've removed the parentheses, it's a good idea to eliminate these negative exponents. And remember, the way we do that is by moving them to the opposite position that they're in now. So I'm going to circle all the ones that have negative exponents, and the ones that are in the top, we're going to bring them down to the bottom, and the one that's already in the bottom, we'll bring it up to the top. And we want to rewrite this without any negative exponents. So when we do that, we're going to have 12 to the third in the numerator times b to the sixth. And it looks like that's all that's in the numerator. And then in the denominator, we're going to have 8 to the third times b to the 15th times c to the 9th times c to the 6th. Okay, now let's evaluate those numerical expressions. So 12 to the third power is 1,728. So you'd have 1728 b to the sixth. And then 8 to the third power is 512. And now what we want to do is combine our like bases. So these two c's can be combined, and the b's can be combined. And then this fraction that's in the front, the 1728 over 512, we want to try to reduce that if we can. Okay, so this fraction actually reduces all the way down to 27 over 8. And you can do that by dividing both the numerator and denominator by 64. So it comes out to be 27 over 8. And now let's do these b's. Now remember, the key thing to remember when you're combining bases where one's in the numerator and the other in the denominator is subtract the smaller power from the larger. So 15 minus 6 would be 9. And then put the answer where the larger power is. So that would be the denominator. So we're going to have a b to the 9th in the denominator. And then for the c's, since they're side by side, they're being multiplied, we will add the exponent. So 9 plus 6 is 15. And that, of course, will stay in the denominator because that's where they both are. So c to the 15th power in the denominator. And that would be our final simplified answer. Okay, the last thing I'd like to go over today is something called scientific notation, which is a way of writing numbers that are really, really big or really very small in a condensed format. And something is in scientific notation if it's in the form n times 10 to the k, where this number n has to be between 1 and 10. So between 1 and 10, and it can't equal 10, it had to be strictly less than 10. And this number k is going to be some integer, so it can be positive or negative. So for example, you could have like 8.2 times 10 to the negative third. That would be called scientific notation because this number 8.2 is between 1 and 10, and the exponent here, negative 3, is an integer. Now, scientific notation can be used on really big numbers, like, for example, the age of the Earth is approximately 4,500,000,000 years old. Now, when you write a number like this in scientific notation, the decimal point always comes after the first non-zero digit as you read it from left to right. So as you're reading this number from left to right, the first non-zero digit is the 4. So the decimal point is going to go right after that, always after the first non-zero digit from left to right. So it'll be 4.5. So let's write that down, 4.5 times 10 to the, and then you have to figure out what the exponent is. Now, since the decimal point is going right there, you have to count from that position how many spaces to where it is right now. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'd be 10 to the 9th power. Now, scientific notation works really well on really small numbers too. Like in this example, look at the wavelength of violet light is 0.0000047 of a meter. So again, to write this in scientific notation, we have to first find where the decimal point is going to go. And so we read the number from left to right, and we find the first non-zero digit is 4. It's going to go right after that, so it's going to end up being 4.7. So the decimal point will go between that 4 and that 7. So it's going to be 4.7 times 10 to the, now this time the power will be negative since it's a really small number, and we have to count back to where the decimal point is right now, how many spaces from where it's going to go to where it is. So 1, 2, 3, 4, 5, 6, 7. So it'll be the negative 7th power.